Hey everybody, so we're going to start a new section of material today about matrix transformations, linear transformations. So let's go ahead, get section 3.1 open, get your MATLAB open and ready to practice. So get all that set up and then restart the video. So I'm assuming that you paused and restarted, and so here we are. And let's just remember some calculus or algebra where we have a function like f of x equals x squared, and I'll just make the note that we call this part on the right-hand side of the equal sign, we call that the function rule, right? The function rule just tells us how to evaluate the function. How do we get the output of the function? Okay, so in linear algebra, we call them transformations. And they're vector valued functions, right? So the input is a vector and the output is a vector. And so that's all good, but it turns out there's a lot of similarities. The main difference is that the function rule for a transformation is defined by matrix multiplication. So we have an associative matrix with every linear transformation, with every transformation that we see in linear algebra. And so suppose we have an associative matrix A that's associated with this transformation. Okay, well that just means that we multiply on the right by whatever vector will fit. And it should be, you should notice that any 4-element vector will work, right? Because we're going to take the top row times this column, and then take the second row times this column. So basically any 4-element column vector is going to work here. Okay, so let's get rid of the ink and push forward. So like I said, the function rule is given by whatever matrix A is equal to. And in this case, we can say the domain is R4, vectors in R4, and the codomain is R2. What do we mean by that? Well, let's jump over into MATLAB to discuss that. Okay, so here I've just entered all the stuff. This is straight from the 3.1 online notes. Okay, and so we've got the matrix A entered into MATLAB. We've got MATLAB awake. And so how are we going to find the domain? Well, the first thing we're going to do is, I said that any 4x1 matrix, any column vector with 4 elements will work. Well, let's prove that, right? So randi is the random integer function for MATLAB, and it's going to create a 4x1 matrix. And the 7 just talks about the maximum integer that would be allowed in the vector. Okay, so this is going to make a 4x1 matrix, which is a 4-column vector. Why am I doing that? Well, if we produce random ones, we'll see which ones can actually be multiplied by A. And notice that we're always doing the multiplication on the right. The vector is always on the right, the matrix is always on the left. Okay, well, and I randomize this. Notice that I get a slightly new vector when I randomize, and notice that I get a slightly new solution, right? I get a 2x1 matrix popping out. So notice that the vector is going to randomize and be slightly different. Hang on, let me get it. Okay, so run section, and notice now that the vector v is slightly different and the output is 7 and -2. And when I run the section again, the vector v becomes slightly different and the answer becomes slightly different. What are we learning? What we're learning is that any 4-element vector will go in, right? So we know that the domain is R4 because any 4-element vector that I randomly select will actually go into the function and produce a result. And what are the results? Well, the results are in R2. They're 2-element vectors. And that's the codomain, and we'll talk about that. You're going to say, hey, domain and range, why isn't it range? Well, it is too, but we'll talk about codomains. But let's jump back. All right. And so the codomain is R2. Why? Well, because the result, when I multiply A times some vector X that's in R4, is going to be some vector that's in R2. Okay, so the range lives inside the codomain. All right, but moving forward, Our second example is, well, we've got this associated matrix. It's the same matrix A as before. And the domain is all the 4-element vectors that can be multiplied by it, so it's R4. But how do we determine what the codomain is, what the range is? Right? We know where the result vectors live. They live in R2. But we don't know if the range is all of R2, or we know it's a subset of R2. But we don't know if it's the full thing or half or a quarter or some or all. We don't know. All right. So it turns out that we actually have one-to-one transformations and onto transformations. And it turns out that if the range is the whole codomain, we call the function onto. And we'll go over that more in the next example. But here is what we're going to ask. So if you're going to find out the range, what if they give you a vector y and say, hey, is it in the range of t? Well, how are you going to find out? Well, we're going to row reduce a matrix. Believe it or not, that's what we always do in linear algebra, it seems. We're row reducing. So let's jump over to our example here. Here's example 2, and we're entering the matrix y, the vector y. And again, please remember that we're asking ourselves, hey, what vectors x are solutions? In other words, if I multiply the matrix A times some vector x, what is the criteria that makes me get -2, 1? Okay. How am I going to find that out? I am going to row reduce the augmented matrix A augmented with the vector y. Okay, so let's do that. Let's actually create this vector y, and there it's created, and here's where we're augmenting it. And I'm calling it little a because we're going to row reduce it, but I just want to show you that this does in fact augment the matrix. All right, it adds y to the right of the augmentation bar, and to the left of the augmentation bar, this is in fact the matrix A, just like we've been using. Why am I doing it? Well, I'm doing it because I want to row reduce the augmented matrix. So I'm just going to move this up a little bit so it's easier to see. So we need to do RREF of little a. And why am I doing this? Okay. Well, a couple of reasons. First of all, if the linear system of equations is consistent, then y is in the range. Why? Well, because if it's consistent, it means there exists at least one x that would be a solution. That could, in fact, be multiplied by a and give me the vector y. Okay, but that's not the only reason. Let's jump back over, see if we can understand this a little better. What's going on? Well, remember that the pivots relate to basic variables, but then the basic variables can be written in terms of the free variables. And the free variables are going to be in 3 columns, right? So I'm going to have 3 free variables. And when I write the basic variables in terms of the free variables, I'm going to have what's going to turn out to be the solution is going to be a linear combination of the 3 free variable columns. All right. So there's going to be infinitely many solutions. There are going to be infinitely many vectors x, right, that turn out so that when I multiply them, the matrix on the left, the vector on the right, they are in fact equal to -2, 1, which is y, right? So it turns out that there's actually infinitely many vectors x that work like this, and I find them here. But how do I know that there is at least one vector x that will work? As long as this linear system proves to be consistent, right? I can't have a 1 equals 0, right? As long as I don't have something like this that can't happen, that can't be true, then I know that the reduced row form, the reduced row echelon form of the augmented matrix is consistent. That's how I know that y is in fact in the range of x. A times x is in the range of t. All right. And so again, we'll be back to talk more about domain and codomain and range in the next video.